Let's talk about curve sketching. So in this video, I want to give you some guidelines for curve sketching. We actually already know how to do all of the little pieces. We just need to figure out how to put it all together. All right. So the first set of things I want to look at is what I call big picture or global considerations. So, if we understand the overall framework of what the graph looks like, that's a good way to start. So the first thing we generally want to do is you want to calculate the domain. So just as a quick reminder, the two things that we worry about for a domain are no zeros in the denominator. And the second thing we care about is no negatives under even indexed radicals. Okay, so when you have a zero in the denominator, a lot of times this will give you a horizontal asymptote. So I'll give you a horizontal asymptote very often. And when you have negatives under the even index radicals, you could just not graph those x values because you're not allowed to have negatives under even indexed radicals. The second thing that we want to look at is symmetry and periodicity. So let me talk about the periodicity first. Periodicity just means the graph repeats itself. So a very common example of that would be like sine of x. Really, all the trig functions, they all are repeating periodic functions. Okay. As far as the symmetry part goes, for symmetry, we know that a graph will be symmetric about the y-axis if f of negative x is equal to f of x. All right. So you may recognize that this is basically saying that f is even. Okay. The other situation that we have is we have when the graph is symmetric about the origin. That's going to happen when f of negative x is equal to negative f of x. All right. So you guys probably recognize that that means f is odd. So the nice thing about having symmetry or periodicity is you could just graph a piece of the graph and then either repeat it if it's periodic or flip it as necessary if it's symmetric. So understanding the symmetry or periodicity would make your situation a little bit more straightforward. So for the asymptotes and the end behavior, we could do the following. We know we are going to have vertical asymptotes when the denominator is equal to 0. And we're going to have a slant asymptote when your function is f of x over g of x, and the degree of f of x is equal to the degree of g of x plus 1. And then you can just divide the functions to find the equation of the slant asymptote. Divide f and g to get equation of the line, which is the slant asymptote. All right. Then the horizontal asymptote is part of what I call end behavior. So when you have the end behavior, there were three cases. Case 1 was you have infinite limits. Case 2 was you have a horizontal asymptote. And case 3 is you have no limit. So an example of the no limit situation was something like y is equal to sine of x. That has no limit. It continues to oscillate, right? So in actual fact, a slant asymptote is also, this is also end behavior. It's like a special case of the infinite limit situation. So maybe I should mention that. I'll put that in as a comment in red. I'll say slant asymptote is a special case of the infinite limit end behavior. Cool. So if you did all three of these things over here, the domain, let me highlight these. The domain, your symmetry and your periodicity, asymptotes and end behavior, then you very roughly know, you have a macro view of what the function is going to look like. So the remaining pieces of information are more detailed or local information, okay? So you could create intervals of increase and decrease. So what I usually like to do is I usually like to just draw a graph, for example. So, you know, you might have like a C1 is one critical value, a C2 is a second critical value. And I don't know what it looks like. I'm just making up an example, but you know, you could draw pictures, draw a sketch with arrows, right? That's usually how I've been describing intervals of increase and decrease. Now, to find the local maximums and minimums, you could use the first derivative test. That's easy when you've already done the intervals of increase and decrease. I'll put in parentheses or second derivative test. But I think the first derivative test is easy enough when you have the intervals of increase and decrease. So you can see we increase and then decrease, so we'd have a max at C1. We decrease and then increase, so we have a min at C2, for example. All right. You could have intervals of concavity. Again, I would draw a sketch. I would use the concave up and concave down nomenclature. So let's say that you have, for example, something that looks like this. And let's say that the second derivative was equal to 0 at this point right here. Then, you know, maybe your curve is concave down here and concave up here like that. That's just an example. All right. Inflection points occur when the concavity changes. Okay. So an example would be what I just drew up here, you know, right there, that point is where the concavity changes because my concavity switches from concave down to concave up, right? And, you know, number 7 actually gives us like a point. So we have inflection points. Those are points that anchor our graph. We have intercepts, the x and y intercepts. These are also points that anchor the graph. So let me write a little note there. These are points that anchor the graph, right? Finally, they ask us to sketch the graph. So when we get together in class later on, I'm going to teach you how to combine, you know, we're going to combine 4 and 6 to draw the following sketch. So if you take a look at, this is just an example, but if you take a look at number 4 over here, I have increasing, decreasing information. If you look at 6, I have concavity information. So I can join these two graphs together. So let me show you how that works for this particular example. I'm going to draw a little number line over here like this. This was my C1 critical value. This is my C2 critical value. This is that inflection point I found. And then the first section of the graph, the first section is going to be right here. And that on that section, my function is increasing and concave down. So I'm going to draw something that looks like it's increasing but concave down. That's going to look like this. So it's not just a straight arrow, it's a curved arrow. Then for the second piece, which is right here, my function is decreasing and concave down. So I draw another curved arrow. This time the arrow is decreasing and curving downwards like this. Okay. Then for the third section of the graph, which is right here, that's in between my inflection point and the second critical value, that's still decreasing, but now it switches to concave up. So I'm going to draw a curved arrow that looks like this. It's decreasing, but concave up. And then for the last section, right here, that's to the right of the second critical value. It's increasing and it's concave up. So I'm going to draw a curved arrow that increases, but is concave up like this. Okay. So then this is what I call the curved arrow diagram, connecting increasing / decreasing info and concavity info. Okay. So once you had all of that, you would just use the anchor points. So use anchor points and the curved arrows to sketch your graph. All right, everyone. We'll look at some examples in class later. Take care.